Okay, so we know that our general form of the rate of change function is change in y over change in x. And now we have a particular function f. We have its rule. We have 3x squared minus x. Okay? So we have a particular rule, 3x squared minus x. And so applying that general form of the rate of change function, we get this. And then we do the math, right? So that's the whole numerator all expanded out, multiplied out, expanded out. Agree with that? Did I make a mistake? 3h squared. Did I make another mistake? Anything else? What are you saying? Yeah? No, minus x plus h means minus x and minus h. Any other, is this, do I have it now? Okay. And then this whole thing is over h. Okay, so now we can simplify the numerator. How does it simplify? No, we can't factor out h yet until we see some things go away. So we got positive 3x squared minus 3x squared minus x positive x. Is that all that's left? So 6xh plus 3h squared minus h all over h. Still doing good? Now that I have all h's, I can factor out h. And when I factor out h, now h over h is 1. And I'm left with 6x plus 3h minus 1. And what does this give? What is this right here giving me? 6x plus 3h minus 1. What does it mean? Yeah.
It's the rate of change is the derivative, but after you put that's if it's not if h is not equal to 0.
No, h can be anything. What does this mean? H can be anything. What does this mean? It still has meaning even with h being anything. Yeah. Yeah, so it's approximate rate of change for the function f, 3x squared minus x. But it would be exact if?
You took out 3h if it equals.
Yeah, so we say if h is essentially 0, or really super small, then what is our exact rate of change function? 6x minus 1. Okay, so look, we started with exact accumulation, and we did a little math, and we have the exact rate of change. Okay? So if I plug what's f of something else? Say f of 7. No, too big. F of 2. And r of f of 2. Okay, I want you to find f of 2. And I want you to find r of f of 2. and then I want you to have a conversation about what those numbers mean, okay? To the person next to you. What's f of 2? What's r of f of 2? Tell the person next to you, have a conversation about what do those numbers mean. Go. Is 10? Is that right? 11? Beautiful. Okay. What does f of 2 equals 10 mean? F of 2 equals 10. What's that? He said the accumulation at 2 units is 10. What do you think? What do you think? So 10 is what kind of quantity? 10 is amount, right? So amount of the quantity, or an accumulated amount. So it could have accumulated in bits up to 10, or we just can think of it as just the value of the quantity at 10. Okay. The rate of change of f at 2 equals 11. So yes, 11 is the rate of change. What does that mean? So what does it mean that the rate of change of the function f at x equals 2 equals 11? This is what does that mean? Has anyone learned anything this semester? What's that? Nice and loud. Nice and loud. Okay, and what does that mean, that the function changes at the rate of 11? Yeah.
At x equals 2, f of x will equal 10, and the tangent line at that moment.
I don't think we've talked about tangent line once this semester. But yes, sir.
That when x equals 2, the change in y is 11 times a factor of the change in x.
Okay. So for what kind of change in x, though?
A small change.
You need a small change in x. Why? Because that rate, as soon as you get away from 2, that rate's going to change. Okay? So yeah, so for someone else, what were we going to say?
I was just going to say that the change in y.
Okay. Yeah, so at the moment x equals 2, for a given a small change in x, the corresponding change in y will be 11 times as big as the change in x. Okay? And so that should at least sound familiar, but from here on out, that's the way you have to think about it. So around 2, for a very small change around 2, you would expect your y would change 11 times as much as whatever your change in x you picked was. Okay? Right. Okay. So let's, we've got lots of ideas flying around here. I want to kind of look at some big picture stuff now. Okay? Look at some big picture stuff. So rate of change and accumulation. Okay, so in the first half of the course, we looked at the situation. You know how fast something is changing, and you want to know how much of it you have. And now, just in the last week or two, we've been talking about, you know how much of something you have, you know you have an accumulation function, and you want to know how fast it's changing. And we're doing pretty good. right? It only took us a week to be able to say, given 3x squared minus x, to find out that that's changing at a rate of, what, 6x minus 1, like the example we just did. Okay, but looking back at the first part of the course. So here's an example. There's something similar in the book, I think. So over on the left, we have the rate of change of elevation as a function of distance from the border. And then over here on the right, we have elevation as a function of distance from the border. Okay? So using the exact rate of change of elevation of function r, write a function f that gives the exact accumulation of elevation starting from a miles to x miles from the border. So I'm going to say, looking over, so this could be anywhere, okay? This could be any starting point, a. I want to know a function using r that tells me the change in elevation from my starting A to any stopping distance x. Okay? Can you do it? So can you write a function f using r that gives me the exact accumulation of elevation starting at a miles from the border to x miles from the border? Go. See if you can do it. Everyone think about it by themselves, and then only if you're lost, ask for help, okay? But so everyone should be able to do this. Okay. How did it go? Let's see. Somebody new. I'm going to start calling on people here. Okay, how about, tell me your name again in the green shirt. Yeah. Ashley? Ashlyn. Ashlyn, how did this go? Did you get it? Tell me. Was it that? How'd you do? Okay, so this is what we talked about. Given the rate of change, and so this was what we did at the beginning of the course. You know how fast something is changing, R of t, and you want to know how much of it you have. And so how much of it you have would be total elevation change, and we went through a whole month of learning that that is represented by integral. And so how is that represented by integral? Okay, what does the integral sign mean? Sum. So this is open form. This is open form. It reflects a process. Okay, we're starting to talk about open form versus closed form. Open form reflects process. This is open form because that integral German S stands for sum, right? So that's S for sum. What are we summing up? What is it we're summing up? Yeah?
You're summing up each moment of rate of change to the condition.
Are we summing up rate of change? Changes in y. We get changes in y from rate of change. That's where the dt comes in, right? So each of these, so it's not that we're not summing up rates, we're summing up mdx's, right? We're summing up mdx's, rate times change in x. And that's what this is, right? Because the change in y is m times the change in x. And we're summing up many bits of those. And so you see how this process is reflected in that open form. That process of we're summing up many, many bits. Each one of those bits is the rate times the change in x. Okay? So now, suppose E is the elevation function shown, okay? So E is the name of the elevation function shown. How else could F be written now in terms of E? Everybody work on it. So I'll come over here, and we're saying now from A to X. Same change, same amount of accumulated elevation. How can that be written in terms of the function E? What could we do? Yes, ma'am.
Would it be f of x minus f of a?
But there's no function f. So no, we want to rewrite f in terms of E. All right, so you got the right idea, but in terms of E, what would it be? Yeah, E of x minus E of a, right? The final elevation minus the, whatever that initial elevation is from the border at a miles from the border. Does it make sense? Okay, so let's summarize that. The accumulation of small changes in elevation from A to X miles from the border. That's the integral. What that process the integral represents is the accumulation of small changes in elevation starting from A miles to X miles from the border is equal to, what is it equal to? So what is this reflecting? If this is reflecting an accumulation of small changes, what does E of X minus E of A reflect? Yeah, the total change, right? So the total change in elevation from A to X miles from the border. Sorry it's so low on the screen. Can everyone see that? Yeah, so it's two different ways of looking at the same quantity. By summing up bits of accumulation, or just by looking at it as a lump sum total amount of change. Okay. Here, this is like the most important concept of the whole course, almost. Okay? Anybody have a question? Does it make sense? So if we generalize that, we have something like this. The integral from A to X, RT dt equals f of x minus f of a. And so if we're just generally talking about what this is the accumulation of small changes of a quantity from A to X. Your independent variable varying from A to X. And this over here is equal to the total change in that quantity as the independent variable changes from A to X. Okay? This is the fundamental theorem of calculus. This is the kind of the pinnacle of the course. Now we don't have everything we need yet, but we have lots of it. All right, so lots of this, and the main idea of it we certainly understand, which is that you can get a change in a quantity by its accumulation bit by bit, or looking at the final value minus the initial value of that quantity. Okay, so now that we're starting to find rate functions from accumulation functions, this all ties together, okay? So here we go. So we just show that if the accumulation function or the quantity function was 3x squared minus x, what was the corresponding rate function that we just found? 6x minus 1. Okay? Now that we have that closed form rate function, closed form meaning it just is a familiar function that efficiently can give you lots of outputs quickly, just a basic formula that you're used to. Now we can answer something like this. We can say, if I have the integral from 4 to x of 6t minus 1 dt, now that we have this principle that we talked about here, before we didn't, but now we know something we could write this as a closed form. instead of writing it in open form like that, we could also write it in closed form, knowing that 3x squared minus x was the accumulation function for this rate of change function, 6x minus 1. Okay, we just have to apply this right here, that the total accumulation of little bits at this rate is the same as the total change from f at x minus f at a. So can you write down now then what this equals? Use function notation in this first step. Use function notation to write down what this would be. Would you use r sub f of x, or would you use f? And what would you write using one of those functions to represent the integral from 4 to x 6t minus 1 dt? Using function notation now. Using function notation. Okay, so are we going to use f or r of f? F, and it's going to be f of x minus f of 4. Look, we're summing up bits of accumulation, 6t minus 1 dt, those are bits of accumulation at that rate, starting at 4, ending at x. So that's just the same as the total change in the accumulation function from 4 to x. That's just the total change in the accumulation function starting at 4, ending at x. And total change is final minus initial. Okay, what is f of x? But we know what f of x is. What is f of x? 3x squared minus x. What's f of 4? What you get when you plug 4 into f, right? 3 times 4 squared minus 4. Okay, so what did we just found? We just found a closed form. This is an easy function rule that will crank out amounts of accumulation, whereas this was more elusive, right? This was open form. We needed GC to help us evaluate that. It reflected the process, but it wasn't user-friendly, right, for getting results. Well, now we've got closed form. Closed form. So this is the closed form representation of from 4 to x, 16 minus 1 dt. Okay, another example. So last time we looked at the volume of a, sorry, that should be x, or this should be r, say. Volume of a sphere. And we did the work. We used the general form of the rate of change function. We applied the volume for the volume for a sphere formula, and we got this for the rate of change function. So when we found that rate of change function, we found two things. We found the rate of change function for volume of a sphere, first of all, but then we also found how we could write an open form integral like this. Okay, so here's an open form integral. Now that we know that the rate of change of f is 4 pi r squared, then we also know what this is in closed form. Go, write it. What is that thing in closed form? Use function notation first, and then find the actual rule in terms of x. Sorry, these should be ours. Let's just do x's. Okay, now my symbols are consistent. Just use all x's. Okay, so the total what is this relative to a sphere? So this expression right here. Can you explain what that is relative to a sphere? Tell the person next to you. What is that expression relative to a sphere? See if you can do it. Okay. Somebody new, what is that relative to a sphere? What is that expression relative to a sphere? Can you? Okay, we need. All right, yes, sir.
Is the total accumulation from 10 order value of x is x being the current radius?
The total accumulation.
Accumulation of volume.
Accumulation of volume. Of the sphere. As what?
As the radius increases from 10 to x.
What do we think? Pretty good. Okay, yeah, accumulation of the volume of the sphere as radius increases from 10 to x. And is that expressed kind of just as a lump sum of change? This just changes, boom, this much? Or how's that expressed? Many, yeah, right. So from 10 to 10.001, find that amount of change in the volume. And then from 10.001 to 10.002, find that a little change in the volume. And then you continue to add up all those bits of change in volume until you get, and then add them all up from 10 to x, okay? So how else can we express, what we're saying is how else can we express the accumulation of volume of the sphere as the radius increases from 10 to x? How else can we express it? Yeah? F of x minus f of 10, the final volume of the sphere minus the initial volume of the sphere when the radius is 10. Okay? And so then f of x equals 4/3 pi x cubed. And then f of 10 is probably very distracting. Okay? That's left over from before. Okay? And so let's kind of make this a little tighter. So 4/3 pi x cubed minus, what is that, 4,000? $4,503. Okay, anybody have a question? This is a huge important principle. Because we're going back and forth, right? So it's like we only spent a week going from what, given the accumulation, figure out what the rate is, and now all of a sudden we're going back the other way again. Yeah.
I think you found like it's like
Is it okay? Oh, that's okay. No, I appreciate that. Yes, I appreciate it. Okay. Any other questions? Any other questions? Okay. So let's look at something from your homework. You had this in your homework. It gave you 3 accumulation or amount functions. F of x, g of x, and h of x, right? X squared minus 2x minus 1, x squared minus 2x plus 2, x squared minus 2x plus 7. Okay? And so you were to find the rate function. So you could use the general form of the rate of change function. And any of those, you could work through the math. And you found that they all have the same rate function. And you found that to be 2x minus 2. Okay, so here I've just graphed f, okay? What is f's rate of change function? 2x minus 2. Okay, so now I have this expression. Okay? The integral from -1 to x of 2t minus 2 dt. Okay? I want you to talk about when I turn that on. So don't do this. So don't do this. I want you to talk and think about what this graph is going to be, how it's going to be displayed if I were to turn on y equals integral from -1 to x 2t minus 2 dt. So computers away, fingers off the keyboards, eyes off the screens. Talk about this. What's going to happen and why? What's going to happen and why? Go. Okay, so let's just focus on the -1. what does it mean that the integral, the lower limit of integration is -1, or the integral from -1 to x? So just what does that -1 going to result on the graph? Yeah.
The graph starts at -1.
Starts at -1. What do you mean? So when you say starts at, okay, no values to the left of -1. Yeah. We're going to start accumulating from x equals -1. So then what mathematically can we say then about -1? X equals -1. Okay. But for the graph now, for the graph at -1. What's the value of the accumulation when x is -1? How much have we accumulated at the starting point? 0, okay? So shouldn't that graph go through the point -1, 0? Okay? So here again, here's, let's see, does this show up? Something light, I need something light. That's good, perfect. Okay, so if it starts at -1, so here, there's f. So, like that? Yeah. Is this what it's going to be when I turn on y equals the integral from -1? Because what? It's going to be the same graph, but it's going to start accumulating at -1 instead of something else. What do you think? Yes? Okay, so someone, if you're saying no, who's saying no? Why not?
Can't that be written as like f, or that integral could be equal to f of x minus f of 1?
If this is the rate of change of f, is this the rate of change of f? Then it can be rewritten as f of x minus f of -1. So is that going to move my f function left or right? So this is f, right? So this accumulation function is basically f minus, what is f of -1? 1 plus 3 minus 1. Is it 3? So how is, I hope that's 3. Just do it. Two. Glad I checked. Okay, so how is this accumulation function? It has the same rate as f, but how is it different from f? Shifted to the left 2. Down 2, right? This is a y coordinate, right? Output of a function is y coordinate. Okay? And so by subtracting 2 from f of x, that's subtracting 2 from every y value, which does what to the graph? No, y coordinate. It's subtracting 2 from every y coordinate. So this is not correct, all right? Yes, it has the right starting point of accumulation, -1, 0, okay? But it's not right. Why? Because this has a different rate profile than this one. We need the same rate, but starting at -1, 0. So we'll turn it on. And I'll turn this one off. So do you see that these two graphs have the same rate of change, 2x minus 2. The accumulation function from -1 to x then has a starting accumulation at -1, the accumulation is 0. So it's the same rate profile as f, but with starting its accumulation at -1 at 0 at -1 rather than 0 at, say, whatever this is, -0.4. Okay. Happy Wednesday.